call the rotor the field windings because it is supplied, as you had seen from the animation, with a DC field, and that produces a magnet with 2 poles, or in the case of that animation, 4 poles, right? So the field is in the rotor, and the stator now contains the armature windings, right? So you would take off the power, which are these windings here, in the form of 3-phase. You would have 3 stator windings that are 120 degrees apart from each other. And the field is supplied from a DC source that you have externally to the machine itself. It is usually supplied through slip rings, but we will see some certain variations in the same. So what you see on the machine is you have a 3-phase supply that is, as we have gotten used to throughout all sorts of mains or 3-phase. It is just a normal 3-phase supply, bearing in mind the fact that the windings have been placed 120 degrees apart from each other. Okay. So just to do another demonstration of that, you would find that generally the windings have a short cylindrical base, and you would have salient poles. That is, they are not a cylindrical rotor, it is salient poles. Each of these represents a pole that is providing magnetic field to the machine, right? And what you see here now, this is the exciter, that is the field windings that are supplied to the machine. Straight away, you notice that the windings themselves are very small compared to the rest of the machine. So what you're doing is you're supplying a small current or a small field, and it is able to generate a larger field that is there, okay? So in some of these cases, what you will end up seeing is you need a different kind of exciter, whereby you would want to have a way in which you avoid having a DC source. Because generally in a power plant, you would already be having a 3-phase power. If these things are connected parallel to each other, these generators or alternators are connected next to each other, you would probably have AC sources around or nearby, so you would be able to supply them. So we are next going to look at the exciter. One of the other things that we've seen is that the frequency of the field supplied will be given by the speed of the mechanical movement times the number of poles over 120. Excuse me. So the frequency itself is only proportional to the speed of the prime mover and to the number of poles. So in the case of a machine like this, you have a large number of poles. You have a large number of poles that are all over the machine itself. That means that such a machine would be able to be rotated at a very slow speed while still being able to create the frequency that we would require, which is of course generally 50 hertz as per the Kenyan standards. So now let's look a bit at the excitation. So field excitation. So what this diagram now represents is the schematic or the circuit diagrams of the field excitation. So on the upper part of the diagram, these sections, you have the rotor. These are all circuits that are mounted on the rotor. And below, you have circuits that are mounted on the stator side. The circuits that are on the rotor rotate with it. So you have the field, the rectifier, the exciter, armature. These all rotate together with the movement of the windings themselves. And you have these, the stator, which are fixed onto the stator, so there is no rotation. They do not move, they are stationary. So you have two of them. You have a field input and you have the main armature, which is the actual output of the three-phase power that you're talking about. Okay, so the main machine itself is, first of all, this section. This is the main operating part of the machine. You have your field winding, which acts as your magnet that is rotating inside the stator. So through the act of electromagnetic induction, through the principle of electromagnetic induction, that movement of the magnet cutting across the armature windings creates a magnet, or rather an electrical voltage, and if you connect a load to it, it will also create an electrical current that will flow through the circuits as an output. Okay. Now you want your magnet here. So how do you create your magnet? You supply IF, which is a DC current. How do you get a DC current? That is what this circuit is for. So you have a rectifier connected to a small three-phase circuit, which has an AC current. Okay. On this side, it is AC, it is rectified, it becomes a DC that flows as IF. This is the field current that flows through the field windings and will be able to give you an interaction with the armature windings so that you have an output. So these windings, if we relate it to the photo that we've seen on this side, these windings are now, apologies. These windings are now the ones that are here. So these are the field windings, and the exciter here is the rest of this circuit that you're seeing on this part, right? So the main field windings are the many poles that you saw in the diagram, and the exciter is mounted on the same shaft as the rotor. So the rectifier and the smaller windings that are supplied are mounted on there. Now, at the same time, how do you get your AC current onto the rotor itself? You have a number of options. You can have, on the stator side, you have a three-phase current that in turn magnetizes another exciter field that passes on to the armature through either not slip rings, through transformer action, right? So you have your DC here, but because it is interacting with windings that are mounted on a rotor and that are rotating, you have this one inducing a current in this field. Okay, so there's an interaction between the exciter field and the exciter armature, and then the exciter armature is rectified to give you the main field. So it is a sequence of input of three-phase AC rectified to DC again, or for the first time. DC induces an AC within the armature. So you're going from DC to AC through transformer action. Then AC is rectified back. It becomes the main field winding or main field current. And then that in turn interacts with the main armature. Okay, then you have your output on that side, right? If you want to make them fully independent, because you still have, you would have a three-phase input that you're putting into your entire machine. If you want it to be fully independent, that is to be self-starting, you can add an extra element whereby you have this section called the pilot exciter that you add to your exciter field, right? So instead of your exciter field being connected to three-phase power, you could have small permanent magnets, which in turn, so you have like the action of a generator here, creating a three-phase AC, then it is a DC, then it becomes through transformer action, another AC here, then DC, and back again to your main armature, and finally you have your full output. Okay, so in that way, it is almost like amplifying. You're building up your currents and your voltages so that they in turn create an output as you are as you require. Remember, the rotor is all of this. Sorry. The rotor it is always in motion. Yeah, it is always rotating. And the stator is always stationary. So the interaction between these parts is what now indicates or gives you your operation of motor or operation of a generator. Any questions so far on that? Any technical challenges? Are we seeing everything? Are we hearing everything?
Yes.
Okay.
Excuse me, I have
Yes.
a question. What's the reason for having the permanent magnet for the pilot exciter field and not just have it at the exciter field?
It is kind of like amplifying. Generally, you would not have magnets that are powerful enough to provide a current that is needed. So it's almost as if it is like a two-stage generator, if I can call it that. Yeah. So each stage builds onto the next stage. Get it? So at the first stage, at this stage here where you have your permanent magnets, the permanent magnets, by their action with interaction with the exciter armature, can generate a small current that is then pushed through. And at each stage, because you're inputting the rotating energy, at each interaction between, let me use a different, at each interaction between, every time you're crossing between stationary and rotational, you are adding, almost like you're adding the energy input of the rotation of the prime mover into that, and that becomes your amplifier. You're converting the rotational motion into electrical energy. Okay?
Okay, thank you.
All right. Okay, so next let's look at the principles of operation of the synchronous generator. Now, so when you have your field that is rotating inside the armature, it generates an electrical voltage. So how does that relate to the principles of the construction of the machine? So what you will find is you have an internal generated voltage, which is what we had, let's go back here, which is what we have here. This in the, not in the armature, sorry. Yeah, in the armature, you have an internal voltage that is generated. This output that I'm talking about is actually a voltage, which we call terminal voltage, right? That is your useful voltage that you can actually take off, and you can have a current in the armature that you can now make use of outside of the alternator. However, within the armature itself, when you have your conversion from rotational mechanical energy through the action of the induction, Faraday's induction principle, you have an internal generated voltage, which we call E in the armature, which depends on a number of factors. So it is given by K pi omega. So your internal generated voltage, which is that, depends on, first of all, the flux. Okay? That is the magnetic field that is coming from your field windings, all right? So we've talked about here that you have an interaction between the two of them. So this DC current that is flowing here, this field current that is flowing here, creates a magnetic field which has a flux called phi. Yeah, it is called phi. So that magnetic field that is here, the magnitude of that field determines the amount of, or the magnitude of the voltage that you will get. Let me just clearly. So this is in internal generated voltage. It is dependent on flux or magnetic field. At the same time, it is also dependent on the speed. We talked of what is the speed of rotation, and that one is what determines your energy that passes across, or rather your voltage that is put across. So the speed of rotation via the prime mover, which we indicated previously, it's related to the frequency, which depends on also the number of poles that you have and the speed of rotation of the actual prime mover. And the final factor that we would need to look at is here what we are calling K. So these are construction factors. These are a number of them. So now that these ones are a way of indicating the construction of the generator that we have. So like in the photo that I showed, you have a large diameter armature field winding, which has a short length. Yeah, if you had a longer length and maybe a smaller diameter, that one has a different impact on the way the internal generated voltage or the magnitude of the internal generated voltage that you have. So some of these construction factors are the pitch. When we talk of pitch, is how far apart are the windings? What is the step from one winding to the next? What is the distance in between? You also have KB, which is distribution, a distribution factor. How closely packed are these windings? You know, are they, what is the nature of their distribution along the surface of the rotor? And then you also have KF, which is the form factor of the windings. Are they square? Are they round? What is the shape of the coils that are there? And finally, you can also have T, which is the number of coils that you have, right? So these are now the main determining factors that will let us know what is the magnitude of the internal generated voltage. By far, the biggest factors are this flux and the speed of rotation. The construction factors tend to alter, I can say, the shape of the waveform, yeah, how regular or irregular it is. But generally, the biggest factors are the magnetic field, and the magnetic field, once again, is determined by the field current, IF, right? So that is a direct way in which you can alter the generated voltage, right? And because of this, you can have a characteristic whereby, try and draw a straight line, a characteristic whereby if you compare the magnitude of the flux and the magnitude of the field winding, the relationship between the two is generally linear up until the point you get saturation, of course, right? So by and large, if you have the field current being varied, you can alter the magnitude of the flux that is available within the space of the machine, so within the field winding. Okay, I think that is clear. So next we can move on to Having known that the internal generated voltage is determined by that, what are the actual parameters of the machine? So like, what is the equivalent circuit of the synchronous generator? So here we have, once again, a cross-section of the synchronous generator, simplified as we had done initially in the past. So you have your stator and you have your rotor, simplified to 2 poles, and it is rotating at a speed of omega m, okay? Because of that, it has a flux that has a value of BR, that is the magnetic field within the rotor, okay? And then you have your internal generated voltage. But before we get to that, right, we need to look at, remember we've said we have 2 different things that we are looking at. I mentioned when we are looking at the output of our generator, what the load sees is a phase voltage. That is a terminal voltage that is available at the 3 or the 4, in the case of a star-connected machine, terminals of our alternator. What voltage does the load see? We are giving it as terminal voltage V phi. But we've mentioned that the internal generated voltage is given by EA. Now, what actually happens during the operation is that your internal generated voltage will not be equal to the terminal voltage. There is a difference between the 2 of them. So your internal generated voltage will never be equal to your terminal voltage. Okay, internal generated voltage, what the windings in the armature are seeing; terminal voltage, what your potential load and output is seeing. Okay, so why is this the case? There are 4 factors that determine that. Number 1 is the shape of the poles. Okay, remember we mentioned when we are talking about the internal generated voltage, we've talked of the distribution, the pitch, the form factor, and so on and so forth. So those have an impact on how the terminal voltage will be passed on to the load. This is either you have salient poles or you have cylindrical poles. In most generators, in most practical applications of generators, you will tend to have salient poles. That is the ones that stick out, which you saw in the video, which you saw also in the photo. Let me just show the photo again. So these are the salient poles that we're talking about, right? Each pole sticks out from the cylinder of the thing. They are not distributed along the rotor itself, right? For purposes of the discussion we are having, we will assume that all our generators in these calculations that we are doing have salient poles, and we will disregard the factor of cylindrical poles. Those who want to go a bit deeper, there's I think there's an appendix I added in the text, or the appendix in the textbook that I added in the Google Drive or the class drive. You can see that, but it is really beyond the scope of what we're talking about here. So that's reason number 1 why there's a difference between the 2. Number 2, which is by far the biggest impact, you have armature reaction. Okay, and we will describe armature reaction shortly. Number 3, you have resistance of armature coils. Yeah, remember you have your internal generated voltage coming across from the stator, or from the rotor to the stator, the field is inducing some voltage within the windings of the armature, within the windings of the stator. Those windings are not perfect. They have a resistance in themselves. You know, all copper, all aluminum, whatever windings you're using will have a resistance. So that has an impact. There's a voltage drop between the internal generated voltage that you find and what is available at the terminal voltage. And finally, you also have self-inductance of the armature coils. So similarly, these two together, this is the impedance of the windings in the stator. Okay, so any equation between the two of them will have to factor in the impedance of the windings as well as the armature reaction. Shape of poles, we have said we will assume salient, so that will not really come into play in our discussions as we look at the equivalent circuit. So let's look at the armature reaction. The armature reaction has the biggest impact on the difference between the two. So let's have a look at it. All right. So here is our cross section of our motor. Now let's assume the motor is running. The field winding is rotating within the space of the stator. So you have your rotor moving in this direction as per what you have. If you have your rotor moving in this direction with the magnetic field in the direction shown, which is that way, you will then have induced voltages in the directions that are shown. So if we assume these are coils or windings within the stator or within the armature, any current that would flow out of the screen in this section and would flow into the screen in these sections that are there in the lower half because of the action of the rotor. We went through this when we were looking at the principle of operation of a rotating magnetic field. It is the same thing that we have here. A rotating magnetic field cutting across conductors, as simple as that, all right? So what you have now is you have a rotating magnetic field that is interacting with the stator. So that field is given by BR. It is in this direction and it has a certain magnitude, right? Now, because of the action of this magnetic field, we have now created an internal generated voltage within these windings, and we call it EA, which has a peak of EA max, right? So those two, because of the interaction of the field with the conductors, the stationary conductors, create now your internal magnetic, or rather internal generated voltage. So what happens next? Let's add a load. What happens when you add a load? When you add a load, you then have an internal current that is induced in the stator that has, you know, a certain flow. So let's call it IA, okay? It has a flow within the windings. So in addition to the voltage, you now have, when you have a load, you have a current that is flowing through the windings, right? Now, this current, depending on what the load is, let's assume we are running a bunch of motors. Let's say this is a lagging current that is flowing, okay? What you will find is your current IA, remember this is a rotating magnetic field. Because you have your current IA, you will then have, in turn, your IA will also start creating magnetic fields within because of the action of a current flowing inside a conductor. A current flowing inside a conductor sets up a magnetic field around it, yeah? For purposes of this diagram, direction will be something like that, okay? The net result of that is that you will have eventually another magnetic field that will sorry, a magnetic field, let me draw it this way, that will have a resultant, say, in that direction. Okay. Right. So let's say it's moving in that direction. And this magnetic field has been created by IA, because IA in itself has created there's a current that's flowing through the conductors, and therefore there's a magnetic field that interacts with this magnetic field that is already there. So this one now is another magnetic field B, but it is because of the stator, right? The armature windings, the current that is flowing through the armature windings creates a magnetic field that is there. Now, what happened when we had a magnetic field within the rotor initially? It came with its own internal generated voltage. The same thing happens here. Yeah, you will now have a voltage that is created, but this is now an armature reaction voltage, and it is a voltage because of the stator, right? So E stator we call the armature reaction voltage. Okay. Remember, this is due to a lagging current because of the load that has been connected. It is drawing a current. There's a difference between those, the current that is flowing and the voltage that created it. So now you have another field that is created, another magnetic field. So in the end, you now have, in this same space, you have your BR and you have your BS together within the same space. What then happens is you end up with a net field here, depending on the magnitude of the armature reaction, a net field which is the resultant of this. Okay, I've not drawn it to scale. Let's call it that. But you know, if you were to superimpose the net effect of that, if you add BS to here, the resultant is B net. Sorry, the scale was not very good. Let me try and retroactively end that. Okay, so let's say BS is that size. And okay, so our BS is here. And when it is, you find the resultant of the two, BR and BS, you have a net B or magnetic field that is distorted. Yeah, so you have a distorted field from what you originally had from the rotor that gives you B net. And what you find is that this B net comes with your own final voltage, which is V phi, which is the ultimate terminal voltage. Okay, and that is the gap between the two. Now, in addition to BS, of course, your current IA was generating the armature reaction voltage. It is creating your armature reaction voltage in the form of the magnetic field that is there. Remember that your IA is flowing through the armature coils. So you then have the interaction of the resistance and the self-inductance. So what we now end up with is you have all the components that are necessary, all the components that form part of the circuit of your, the internal operations of your electrical machine or the synchronous generator. Okay. Any question on that? Are we getting how the armature reaction distorts the field? Okay. So what will eventually happen is you have a E start, the voltage here can be represented by an X, a certain inductance due to the armature reaction. All right, we represent it by an X there times the current IA, right? Because it interacts, it is due to IA and it interacts with the others. So when you put it as in terms of a voltage, you create this element that will be able to put it into the form of a voltage. So now you have your voltage V phi, which is given by EA plus E start, right? Because you have, remember that the V phi is the resultant of the net magnetic field, which is the initial magnetic field that you had plus the armature reaction voltage, or rather the field due to the armature reaction, right? So this then becomes EA minus JXIA, okay? So if we want to now also include the impact of the resistance and the self-inductance of the coils, you then have an additional one. So this element is due to armature reaction. It is the representation of armature reaction. You will also have to now subtract again a value JXAIA, where XA is the self-inductance that we talked about of the armature coils. And in addition to that, you will also have to subtract X, not X, this is R, which is the resistance, RA times the current that you're flowing through the armature, which is the resistance of the windings. So having put all of that together, we are now in a position to indicate what is the actual representation of the internal generated voltage. So we have it as, if we take it to the other side and have your terminal voltage on this side, it can be V phi plus J times XIA plus J times XAIA plus again, sorry, there's no J there. That is the resistance. It's not it's a real element, not a reactive element. So RA I, right? So now you then have all the components that you would need to create an equivalent circuit of your alternator or your synchronous generator. Now, for convenience, we tend to combine these two inductive elements, whereby we give them a value called the synchronous reactance. Synchronous reactance, which is equal to the sum of the two. Okay, so the reactance due to armature reaction and the reactance due to self-inductance of the windings themselves, right? So your final equation would look like EA equals V phi plus JXSIA plus RIA. Or in other words, V phi is equal to EA minus JXSIA minus RAIA. So you have a circuit that looks something like this. So the equivalent circuit we can now draw would look like this. So, of course, this is a three-phase machine. So this would be EA1, V1, so on and so forth. So you would have actually three of these windings, all where you have EA1, EA2, and EA3. So you have three windings with all the elements that you are talking about, RA, and you have three phases, V5, 3, right? So this is the armature side. To complete the circuit, we can indicate on the field side what are some of the elements that you have. Sorry for the roughness of that. So this would be RF, the resistance of the field windings. This would be XF, the inductance due to the field windings. And over here, we can have now an adjustment resistance that allows us now to play around with the value of the field current. Remember, we said that the amount of the internal generated voltage, EA, is directly proportional to IF, as well as the speed of rotation and, of course, the construction factors. So this IF is regulated using that resistance that you have there, right? Then you'll have, of course, a VF on that side. So this is essentially your equivalent circuit of the synchronous generator, okay? So at the same time, let's look at a couple of additional characteristics of the this electrical circuit that we have here. So let's take a look at one of these elements, yeah, so that we look at what do the phase diagrams look like. Let's draw the phase diagrams. This we can call the equivalent circuit. This is your very important equation, and that was your derivation. Okay, so we are all here together. Right, so the phase diagrams. Remember that we have two main voltages that we're looking at. We had our EA, the internal generated voltage, and you have your terminal voltage, the internal generated and the terminal voltage. So now let's take the terminal voltage to be our baseline, to be the initial, sorry, my lines are not very straight. Try and get a better one. Okay, slightly better. So that is your terminal voltage. Let's call it V5, okay? We are assuming it is at 0 degrees angle, and we are assuming it is our baseline, which we will use to take the same. Now, if you have a load that has unity power factor, okay, so it is at the same power angle as your terminal voltage. So let's say it is just in parallel here. Let's call it IA at unity power factor, right? They are parallel to each other in the same direction. What happens to your other elements? So you have your current IA, let's indicate it here. So your current IA flowing through your entire circuit, assuming we add a load that looks like that, right? So you have IA flowing through, you have a terminal voltage which is seen across these points, and you have your load, which we have added there, right? Internal generated voltage is our source. Now, the IA interacts with the RA, and you have a voltage drop in that point, okay? So this is IA, RA, okay? RA, or rather the resistance, does not alter the direction of the current. So you have IARA, which is your voltage there, can be added, and it will look like that. Okay? So that is the potential drop due to this element RA. Potential drop due to JXS. Straight away, you have your complex or your reactive element. So that means that your potential or the voltage drop that you have there will be at 90 degrees because of your J. It will be at 90 degrees to your current IA. So in that case, you draw it at 90 degrees and you have JIAXS, right? So remember we said your internal generated voltage EA is equal to the sum of the terminal voltage, the combined synchronous reactance times current, and the resistance times the current itself, which we have indicated here. Okay. So the resultant EA is actually, if I can get a straight line here, it's actually from there to there. So you have EA being the resultant of all these elements. You have your terminal voltage, your resistance of the windings, and your synchronous reactance, the combined synchronous reactance. So there will be an angle between the internal generated voltage and the terminal voltage, right? This is for unity power factor, not the magnitude that we are having. Let's say now we have our load, instead of unity, it is at lagging power factor, right? Let me attempt to draw the voltage same way. That is V phi. And you have now, because you have a lagging power factor, let's say our IA now has an angle to it, right? So they are now not parallel to each other the way the voltages, they initially at unity power factor they were. So now there is an angle. So what does that imply? It means that this element and this element now have a different direction. So the resistive element is in parallel to the direction of the current that was there. So it looks like that, in parallel to each other. Okay, let's assume that is parallel. Reactive element is still at 90 degrees. So we'll call it 90 degrees like that. Looks like that. So this is IARA, and this is JIAXS, right? Let's call this IA1 and IA2. This is EA1. So what you will see is, excuse me, a lagging power factor leads to an internal generated voltage that looks like that, right? So EA2, right? So straight away you can see when you compare the two, the magnitude of EA2 is much more, and also the angle at which it is being generated is less to compensate for the current changes that are there. So why do we take the terminal voltage as the fixed? Practically in the engineering scenarios, you would want a fixed terminal voltage. If your client is expecting 415 volts, you need to give them 415 volts. And that 415 volts would be the terminal voltage. As we said, what the load actually sees, yeah? What the load will see is the terminal voltage. So you want it to be 415. So it means that if your load changes power factor, you have to vary your internal generated voltage accordingly. So if you have unity internal unity power factor, internal generated voltage is at this level. If you have a lagging power factor, internal generated voltage is at that level. So it means that you have to go back to your machine. In order to change the internal generated voltage, you have to now change your IF. So how do you do that? This is where now we have your resistance or your methods of changing the magnitude of the current that you have. Okay? So that's what you have to understand. Similarly with leading power factor, just for completeness, let's talk of leading power factor. You have your same terminal voltage, but in this case, IA3 now has a leading angle. So what does that mean? You will then have your you will then have your IA-RA looking like that, IA3-RA looking like that, and your IA2XS, IA2XS times J, looking like that. And what that means is you now have EA3, which is actually at a much smaller, the magnitude or the length of this vector is much smaller than what we've seen. When you have a lagging power factor, you need more or higher voltage to produce the same terminal voltage. But when you have a load with a leading power factor, the terminal voltage, to retain the same terminal voltage, you can afford to reduce the magnitude of that. However, you have to have a much greater power angle between the two. Okay, so those are now factors that are needed. So now what you will see is when you have a lagging power factor, you need a large field current, and when you have a leading power factor, you don't need as much field current as we saw before. Okay, so that's essentially the equivalent circuit and the principles of operation of your synchronous generator. Any queries so far? Okay, so what we will now do, let's wind up with an example of what we will look at. So you have a three-phase star-connected alternator that supplies a load of 10 megawatts, right? The load is lagging at 0.85, and we want a terminal voltage of 11 kV. Calculate the line value of EMF, so the internal generated voltage, which was EA. Okay, that's what we are looking for. So EA is what we are trying to find. Okay. Right, so straight away, what is the output current that we have? The output current is equal to the power over √3 times terminal voltage times power factor. Okay, or let's call it cos phi. It's cos phi, right? And that is given by 10 times 10 to the power 6, which is 10 megawatts that we have here, divided by √3 times the terminal voltage, which is 11,000 times, some people still joining us, Fula, times the power factor. So let's do that, 10 exponential 6 divided by √3 times 11,000 times 0.85, right? So that gives us 617.5 amps roughly. Okay, so that's the current that is now flowing through your circuit. Okay, now what is the phase value of the terminal voltage? Let's give phase V phi. It is given by 11,000 divided by root 3, which is 6,350.85 volt. What is our value of phi itself? So phi is cos inverse of 0.85. So it is 31 point, let's say 8 degrees. Okay. Right, so we are moving that along. We want EA. So EA is given by V phi plus IA RA plus JIA XS. We can combine these two so that we have V phi plus IA into RA plus JXS. Okay, so let's try and see what that is. So EA will be given by V phi. We've seen it as 6350.85. This one is at an angle which we will determine later on, plus 617.4, got up, 0.5, sorry, 0.5 into RA is 0.1 and XS is 0.66. Okay, so now we have all of those together. So you have 6350.85 plus 617.5 times 0.1 plus 0.66 I should give us what we want. That is 64.6 plus J 407.55. Let's put it into polar form. So it gives us 6425.5 at an angle of 3. Wait, I went wrong somewhere. We needed to include the angle, sorry, that angle that we calculated, 31.1.8. Okay, so actually actually 5459.3 plus 3754.16 or 17, and if we change that to polar, comes, yeah, so it is, sorry, 6625.5 34.5 at an angle of 34.5 degrees. So that is our EA. And the line value of that will be root 3 times EA, which is 6625.5, which is equal to okay, so that's our final internal generated voltage. So in order to produce, remember we want a terminal voltage of 11 kV. In order to produce 11 kV, you need to set your field such that the internal generated voltage is 11,475 at an angle of 34.5, right? Which we saw at this side. Let me minimize that. Which we saw here at the phase diagrams at this point. So a lagging PF, yeah? So if this is 11 kV, this is now 11,500 or whatever it is, kV. Okay, so you have a greater internal generated voltage, also at an angle that is greater than what we had, right? So I think we can stop there. That is our introduction to synchronous generators. Next lecture, we'll look at a few other things. I will try and get the I'll try and get the recording out to you within the next couple of days. So then we'll see from there. Any final questions that we would want to ask?
Excuse me?
Yes.
Why did you change your value when calculating EA from 6412 to 50 something?
Which point?
Why did you change your value towards the end of the example?
Why did I change my value?
Yes.
Okay, at which point? You've said?
EA.
Uh-huh.
There, just there. Why did you change from?
From?
You had obtained 6412.6 and then you
right. Okay, so that one, yeah. Remember, okay, let me then indicate it in red. Remember we said the angle, so sorry, that was a mistake on my part. So you have your voltage, terminal voltage looks like that. And you have your internal generated that looks like that. Okay, so remember now you had your values that you added in between. So you have your IA that was lagging in between, right? So that's the angle that we're including in between. So we added it here, right? We added it here.
Wait, so we're taking IA to be our 0 degree, or?
No, actually, you have a point, by the way, because IA is the one that has that angle. IA is the one that has this angle of 31. Okay, so EA should have its own different angle. So actually, if we do, we said IARA should look like that, and then IARA, JIAXS looks like that. So actually, I may have been right in the beginning, because you have EA is at an angle that is unknown. However, this 6350, the voltage is taken as 0 degrees. Yeah. This is V phi. Okay. So actually the initial, yeah, you're right. The initial calculation I had done, let me just bring back the calculator.
Excuse me.
Yep.
So shouldn't you add like the 31.8 degrees to the 61.617.5
To get your
to get the current, because the current is lagging the phase voltage. So like 617.5 angle negative 31.8 times 0.1 onwards.
so you would add it to this.
Yeah.
Okay. Yeah, at some point it has to come in because you're trying to get EA on this side. So the angle IA 17, so it would have to be at an angle of 31.8, which was there. So it's actually so we would say the angle needs to be added here, right?
Yeah,
It should be
negative.
Negative here. Yeah. Negative there. So that now on the other side, it goes that way. Let's see what that gives us. So we've said 6350 at an angle of 0 plus 617.5 at an angle of, angle of negative 31.8 times.
You've written one.
Huh? Sorry?
The angle, I think you've written 1.8.
31. Huh? Okay, 31.8 times the bracket 0.1 plus 0.66i. Okay, what that gives us. 6618. So it is 6625. The same, but the angle, because the angle is measured from terminal voltage. Terminal voltage is the baseline. That is where our difference is coming in. Yeah. So let's change this back to okay. So actually that was a very good catch. Actually, you have quite the same. Although the magnitude remains the same, but the angle is different. So you have 6618 point, let's say 1 plus J 313.83 volts. Now that is the value, but the angle comes 2.715 degrees. Okay. So actually magnitude remains the same. However, the angle that we have, because we are measuring the angle from here, actually this makes more sense because the angle wouldn't be that big. So this would be match the colors, 2.7 degrees. So that actually your total angle is 34.5, which is in between the two, which is what we had before. So instead of 34.5, which was total angle that way, the only thing that changes is those 2.715. 2.715. Okay, thank you for that. That's a good catch. In fact, I should change it in my notes, meaning I taught last year's group the wrong thing, but I'll change it in the notes. 2.715. Okay, any other questions? If there are no other questions, we can leave it at that. I think we had agreed that the lectures will generally be these Friday morning lectures. I don't know what happened with the link, so maybe what we'll do, if I cannot join, I'll be sending another link. Thank you for moving across very quickly when we started, but I hope next time we will have resolved that issue. So thank you. We'll leave it at that.